Right, over to you guys. Over to you guys.
Okay, so Todd, you're up.
Thank you very much, Michael, for keeping it so short and sweet and maximizing our time.
What can I say?
I'm delighted to be here virtually to our students in Australia, and thank you so much for coming today. Bob and Jackie are dear friends to us and are huge fans of JPL and NASA, have come to the U.S. many times to the space camp in Alabama. If you don't know, JPL is one of 10 NASA centers in the country, and we don't do much with human spaceflight. We'll talk a little bit about human spaceflight towards the end of the talk, just because there's some very exciting news there from a former JPLer and a good friend of mine who may end up being the first woman on the surface of the moon in 2024. We'll talk about that a little later. But JPL, we do a bunch of Earth science. We do space astrophysics kind of missions. But what we've been known for, really for decades, probably more than even those two, are planetary missions. And because of poor Pluto's emotion, so sad it was knocked off the list of planets, we can confidently say JPL's been to all the planets in the solar system. And I've been here 30 years working on many of these missions. Today I'll just kind of focus on some of the flight paths and trajectories a little bit. I'm a propulsion guy, so there's a navigation team and orbital mechanics people that probably understand this stuff better than me. But it's kind of fun to think about because I know some of the three topics that they were looking for a speaker for were gravitational field, space travel, engineering, science. And so I won't be covering things like gravity waves and things like that today, although that stuff's very interesting too, and JPL thinks about that and plans missions. I'll just talk about it as it relates to the missions I've worked on over the last 3 decades. And right, you can see at the bottom there, I'm presuming tomorrow will come in California. It's still the 10th of December here, but I forward dated it to the Australia date. So happy December 11th and happy Friday to everyone in Australia. Currently, I'm juggling 3 missions. I'm a propulsion engineer on Mars 2020, which is a rover we launched in July and will land in mid-February. Wish us luck. We're about 2 months from landing. And it's my 4th Mars rover that I've worked on. I worked on Spirit, Opportunity, and Curiosity, and this is number 4, Perseverance. I'm also on a mission called SMAP, Soil Moisture Active Passive, an Earth orbiter. We measure the soil moisture percentage around the world every 8 days, every place on the solid Earth, so we can predict things like droughts and floods and when to plant crops and track mosquito-borne disease and all kinds of amazing things. Even might help with tornado forecasting. And then my 3rd mission, unbelievably, is the Voyager mission, which are the 2 most distant human objects launched in 1977, 43-year-old spacecraft, twin spacecraft that are still going. And I'll end the talk with some discussions of Voyager and their trajectories. So next slide, please, Michael. So let's start simple. Let's elevate above the plane of the planets. Well, even before that, just I'll go back one. Sorry, I forgot I put that slide in there. So there's the family portrait. It's so hard to get all of the family together for the Christmas card, but there we go. Front steps of JPL's main building, and we've come a long way. So Sojourner's the rover from 1997, cute little rover about the size of a child's wagon or a microwave oven. Spirit and Opportunity were the twin rovers in 2003. About the size of a golf cart. On the left, we launched 2 rovers. They were supposed to last 90 days on Mars. Spirit lasted 6 years into its 90-day mission. Opportunity lasted 14 and a half years into its 3-month mission. So well-built, beautiful American vehicles there. Not nearly as big as Curiosity, which was the rover from 2011-2012. Landed August 2012 and is still going 8 years and change past launch into its 2-year mission. And on the lower right, I'll point out the holes in the wheels there. Those holes allow you to leave marks in the Martian soil. It is a half-meter diameter wheel. So what we know is that 0.5 times pi will be the distance between the holes on the Mars surface if it's not slipping. So if it's less than that, that means the wheel's slipping. And how beautiful. The rover can take pictures of its own hole marks in the Martian sand. calculate the distance between them, figure out the slippage, and if it's too much, it stops so it doesn't get stuck in the sand. And it can do all that without us interacting from Earth because of that pesky Albert Einstein. The signal to get to Mars takes 4 minutes one way at minimum, up to 24 minutes maximum. So if we had to wait to see the results of driving, and the driving, by the way, is 5 centimeters per second, max speed, about like a fast snail. So imagine the problem of getting stuck. This takes the human out of the loop, and that pesky Albert Einstein, the 8-minute to 48-minute round trip speed of light delay. So it can diagnose its own slippage. Now, we love this rover. We had it full of JPL NASA bumper stickers. NASA was not pleased by that, made them take it off. So we started driving around Mars, and then someone from NASA actually noticed those weren't random holes in the wheels at all. They actually spell out JPL in Morse code. So not that we're full of ourselves, but every 0.5 times pi meters on the Martian surface for tens of kilometers, it says JPL, 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 JPL. So NASA headquarters was a little bit steamed at us, but we probably snuck JPL onto the new rover somewhere. I don't know where it is. Maybe we'll figure it out once we land on Mars, hopefully successfully in mid-February. So I've worked on all these but Sojourner, and I am not showing Perseverance, the new Mars rover. Next slide. So I don't have a trajectory plot for Perseverance, but it's always the same. Let's start simple. So we're going to float above the plane of the planets. The sun is the yellow circle, the yellow dot, sorry. And then the blue circle around there is Earth's orbit around the Earth, and the reddish kind of elliptical ellipse is Mars's orbit. So every time we've gone to Mars, we've done the same thing, which is called a Hohmann transfer ellipse. It's half of an ellipse, and it starts there Earth at launch and goes to Mars at arrival. So that's half of an ellipse. It's tangent to the Earth's orbit on the inside and Mars' orbit on the outside. That's called a minimum energy path to get to Mars. And Kepler and Newton figured this stuff out, that even though it's not a beeline straight path, in space going straight is not the minimum energy. It's the best path you basically boost the energy to get on that elliptical orbit, and it's about a 6 to 9 month journey. For our case, for Perseverance, it's only 6 months. This was about 8.5 months in the case of Curiosity back in 2011, 2012. We do TCMs, trajectory correction maneuvers, 1 through 6. If you're a golf fan, this is about a 500 million kilometer par 6 hole. We almost always get so far we've got at least what's the term? An eagle 2 under par, because it's a birdie's 1 under par, eagle is 2 under par. We've never done TCM 5 or TCM 6. And knock on wood, we won't have to do that for Perseverance as well. So we're traveling about 1.5 million kilometers a day, so even if you have a bad day, you say I did 2 round trips to the moon today. That's pretty good. So we're on a very similar path now to get from Earth to Mars for Perseverance. So that's the easy kind of gravity path to start, a very simple Hohmann transfer ellipse. Next slide, please. So things get more complicated when we get to something like a Galileo, and this was my first job. This is the first Jupiter orbiter. It launched in October of 1989. I finished up my master's degree about a year later and immediately joined JPL, and they threw me on the flight team and for a 6-month stint before I did other work, and my 6 months on Galileo turned into 7 years because I loved it so much. And the red path is how we got to Jupiter with this heavy spacecraft. It was too heavy to go straight to Jupiter, so we had to use this cool technique called gravity assist, where we actually fly by the planets and their gravity slingshots us to the next planetary destination. So again, looking down on the plane of the solar system, the sun's in the middle with the rays. There's Venus's orbit is the first circular orbit you see, then Earth's orbit, then the dusty-looking regions, the asteroid belt, finally Jupiter is the large outer circle. And then the red path is how we got there. And in one of the most bizarre twists in planetary science, we looked at 10,000 possible paths to get to Jupiter, and the best way to get to Jupiter was actually not speed up, but to slow down and fall in towards the sun. So you see launch there, where we actually went closer to the sun and did the first Venus flyby in February of 1990. And that's over on the left side with the arrow. that put us in an orbit that went outside the Earth's orbit a little bit, as you see, but then we actually came by and flew by Earth in December of 1990 and took pictures of the Earth. That was really cool. And that put us on that second red ellipse going around the sun. And notice that ellipse just touched the inside edge of the asteroid belt. So we actually did a little dogleg in the asteroid belt and took the first ever pictures of a main belt asteroid. And that's the asteroid Gaspra there. And how cool. I mean, I wasn't even a year into my career, and I'm already helping take the first picture ever of a main belt asteroid. I couldn't believe it. Now, we still didn't have enough energy to get to Jupiter, so we fell in back towards the Earth and did another Earth flyby and took an Earth-Moon movie there in December of 92. And then that finally put us on this leftmost red path, elliptical orbit, where we had enough energy to get out to Jupiter. And then it took another 3 years, from December 92 to December 95, to get out to Jupiter. Once we're out there, we slammed on the brake and then ended up in Jupiter orbit with a bunch of different orbits, checking out the 4 moons over there on the right, Io, Europa, Ganymede, Callisto. Io, the most volcanically active body in the solar system, 10 or 100 times more volcanically active than the Earth. Europa, the ice crust world, with 2 to 3 times the amount of liquid water underneath an icy, water-iced crust. So there might be subsurface life in that ocean. And Galileo helped reveal all these moons and worlds for the first time. Oh, I forgot to mention, back going through the asteroid belt in 1993, we did the second asteroid flyby, Ida, and it turned out to have a cute little moon named Dactyl there at the left. So it was the first ever discovery of a moon of an asteroid. We thought we had one quiet year to catch our breath on this project. It was not meant to be, because Comet Shoemaker-Levy 9 flew too close to Jupiter. Jupiter's tidal force broke it apart and then collected all those comet fragments on a subsequent orbit for a crash into Jupiter. And as far as we know, in the entire universe, other than potential aliens, we had the only front row seat in the universe from Galileo to see those fragments actually hit when they crashed into Jupiter, because we were far enough out we could see around the backside of Jupiter. So that shot there shows an explosion in Jupiter's night sky from one of those fragments hitting the Jupiter's atmosphere very fast. And the fireball's bigger than the Earth there. So our one quiet year disappeared before we got up to Jupiter. What a cool trip, though, and a great introduction to gravity assist and all these crazy trajectories to get this heavy spacecraft out to the giant planet Jupiter. Next slide, please. So how does gravity assist work? Well, before that, since it worked so well for Galileo, we decided to do it for Cassini. And Cassini was my job for 20 years, a Saturn orbiter, the first Saturn orbiter. I was the head propulsion guy on this mission. And again, Cassini way too heavy, 7 tons. We couldn't get it straight out to Saturn. So we did this crazy path where we launched, flew in by Venus. That put us on the first full red elliptical orbit there. We did a Venus 1 flyby, a Venus 2 flyby, and then by the Earth in August of 99. And that finally gave us enough energy to get to Jupiter. And then sure enough, we timed it so we could go by Jupiter and let Jupiter's gravity slingshot us out to Saturn, which then took another 3.5 years. So it's a 6.7-year trip, about 4 billion kilometers. We'd never get out there without this. This was called VVEGCA, Venus, Earth, Jupiter Gravity Assist Trajectory. That's quite a mouthful. But it's the way to get out these heavy spacecraft to the outer solar system. Once we're in Saturn, we capture into orbit, but check out what we did then. Next slide, please, Michael. Well, now, okay, I'm all confused. Now let's explain gravity assist. Because we are seniors in high school, so we've probably had trigonometry and we've probably seen the law of cosines. And we've probably wondered, why the hell will we ever learn this? Because when will we use law of cosines in real life? This is exactly where law of cosines are used. And I told my high school trig teacher this, and now she teaches it in her classroom for a real-world practical application of law of cosines. And here's what happens. So let's look at a Jupiter gravity assist like Cassini did on its way out to Saturn. So when you're coming in from the bottom center, moving to the upper left, you get bent by Jupiter's gravity. And it's a hyperbola. And from Jupiter's point of view, the speed you had coming in is the same as going out on those asymptotes. At plus infinity and minus infinity, it's a certain direction, which are the asymptotes of the hyperbola, and the speed is the same. You can't gain speed with respect to the planet. Of course, while you're flying by the planet, you're speeding up. Jupiter's gravity is pulling you in, speeding you up, but then it slows down on the way out. But what matters is not the spacecraft speed with respect to the planet. It matters spacecraft speed with respect to the sun. And that's a vector. That's the sum of two velocities, vectors. It's the spacecraft velocity with respect to the planet plus the planet's velocity with respect to the sun. And in this diagram, the sun is at bottom and Jupiter's moving to the left, going counterclockwise around the sun. So that's that fixed gold vector in both vector diagrams. But look what happened. The spacecraft velocity with respect to the sun is the blue vector. It's the sum of those other two vectors. And because of the rotation in the spacecraft velocity vector around of the spacecraft with respect to the planet, it hasn't gone any bigger, right? But it's rotated. The black vector has tilted. And because it's tilted, when you add it to the gold vector, you get a different direction. But more importantly, you get a longer vector, law of cosines. You've increased your speed with respect to the sun. And that's how you get out to Saturn. So it's amazing. I think I covered all the words on there. I wasn't looking at my words. I was just looking at the chart. But now, the weird thing, doesn't it seem too good to be true? You've added thousands of kilometers a second to the speed of the spacecraft. I thought energy was conserved. I've had high school physics. Well, the answer is it is conserved, and don't tell anyone, but we actually slow the planets down when we do this. And that's how energy is conserved. Including, remember I said we flew by the Earth with Galileo and Cassini. So don't tell anybody we slowed the Earth down. Now, it's a few centimeters every couple 100 million years, so no environmental impact statement this time. It's okay. Earth took one for the team. It'll be fine. But that's how this massive, amazing technique works. And not only does it work on a planetary scale, it works once you're in orbit around a planet if you can use the moons of that planet to shape the trajectory and do gravity assist. Next slide, Michael. So now is when let's look at Cassini, what happened. So once we're there, we did a 4-year set of orbits, 75 orbits around Saturn. And on the left shows that from above. So these are called petal plots. They look like petals of a flower. And on the right is the view kind of sideways. So not all of these orbits were in the Saturn ring plane. Some of them were up above the poles. So you see Saturn like a bullseye. And you can use the gravity of Saturn's large moon, Titan, second biggest moon in the solar system, to change their trajectory. If I tried to do this tour with rocket fuel, I'd need 100 tons of rocket fuel, and I only had 2 tons of rocket fuel. So that's the beauty of this. It might put a propulsion guy like me out of work, but we love gravity assist. It enables these beautiful paths and trajectories, and they're almost more art than science, but this is literally the path Cassini took for its first 4 years. Now, we had a third of the propellant left fuel after we got into orbit. We did the 4 years. We had 10% of the propellant left. And they said, what do you want to do? Well, let's do 2 more years because Saturn's rings are going to disappear as seen from the sun and the Earth. It's called the ring plane crossing. And next slide, please. And we called that the ring plane orbits, the equinox mission, because equal day and night. Look at those beautiful orbits, high inclinations, pi transfers, high northern latitudes. So Saturn sits there. You can see we had a whole bunch of other elliptical orbits around Saturn over those 2 years. That took the gas gauge from 10% to 5%. The gas light's certainly on for your petrol there. And they said, what do you want to do? And the scientists all said, we want to go another 7 years. We said, are you crazy? 7 years on 5% of propellant? But we found a way to do it, and by using gravity assist again. And next slide, please. This shows the next 7 years and the crazy sets of 100 more orbits, a couple hundred more orbits. And they were highly inclined. Some are in the ring plane, some are really high, but the really weird ones are the red ones. Those are the proximal orbits. Next slide, please. Look what we did. We used Titan's gravity. We jumped the gap. We flew by Titan, and that put us on those blue orbits where we actually passed between Saturn and its rings for the first time. And you have to jump across it in one fell swoop, because if you try to go through the rings, it kills your spacecraft. So we did 22 orbits over 5 months on those blue orbits. And then the very last one actually flew by Titan, and that was called the Kiss of Death, because that made us, it put Cassini on a path that impacted Saturn. So it would burn up in the atmosphere What are you doing to my baby, my beautiful spacecraft? Well, we had to do that. It had to take one for the team, vaporize in the atmosphere because it had bacterial spores on board that might have crashed into one of Saturn's interesting moons, particularly Enceladus, a tiny ice ball. This would be geologically dead and boring. It is not. It has water, ice, volcanoes, and geysers that spew ice crystals into space, and a subsurface global water ocean with hot smokers, hydrothermal vents, the very place where life might have started on Earth. So we could not risk Cassini, bacteria from Earth, hitching a ride on Cassini, contaminating that moon. So that's why we had to come up with this orbital dance to crash Cassini on purpose. And by the very end, I can confidently say as the lead propulsion engineer, the head gas gauge, if you will, the petrol gauge, I can say we crashed into Saturn's atmosphere with 1% of the fuel left, plus or minus 2%. So we were literally running on fumes, and happy to say we made it. Godspeed, Cassini. What a heck of a journey. 292 orbits over 13 years using this intricate gravity assist dance. Next slide, please. Now for something completely different. These are all what's called ballistic trajectories. You basically do a large rocket burn and then you just coast. And that seems kind of wasteful in one sense, right? Why not keep using fuel? Well, you run out of fuel really fast unless you use something like an ion engine that gets 10 times better gas mileage than a chemical rocket. And that enables you to do things you could not do with chemical propulsion missions. And it includes here the ion mission called Dawn, which I worked on also in the mid-2010s from like 2014 to 2018. So look at this. The sun's in the middle again, yellow ball, Earth's orbit, and then Mars orbits in red circle. And then we headed to the two biggest main belt asteroids called Ceres and Vesta. And this is a very different looking path, right? We kind of slowly spiral out. And what we're doing here, anytime where the blue is being seen, we're thrusting the ion engine. And xenon, when it ionizes, has a blue-green glow. And when it's not blue, we're coasting. So we thrust, coast, a low thrust trajectory. So we're slowly building up orbital speed. Notice we did that till we got out to Mars, stole a little gravity energy from Mars there in February 2009. That put us on this orbit that just kept creeping outwards from the sun till we arrived at Vesta, the second biggest main belt asteroid, July 2011. Then we slowed down, matched Vesta's orbit, went into orbit around Vesta for a year, mapped it, studied it, and then we left Vesta. We see Vesta departure up there in upper right. So we stayed a year at Vesta and then started spiraling out again. And then we got out to Ceres at the very bottom, March of 2015, the biggest main belt asteroid. And there it is on the left with that weird salty deposit in one of the craters that proves it, too, was geologically active and erupted kind of salty ice volcanoes. Really crazy place. And we stayed in Ceres orbit for years then, mapping it, and then ended our mission when we ran out of fuel, October of 2018. But that's a completely different path and way to get somewhere than chemical rockets. And it was an honor and privilege flying that mission as well. Next slide, please. Okay, here's a little Voyager video. I want to talk about my new job for the last few years, and I'm so excited by it. Michael, do we know if audio is going to work or not?
You would hear it now if it was.
Not hearing anything.
Yeah, so Todd, all you.
Okay, so I'm trying to remember. I've only seen this a couple times. I'll try to remember what we're saying. I'm glad there's some captions. That'll help. And we'll see this in the trajectory. But Voyager was amazing. Voyager was a mission. Here we launched in 1977 on a Titan IV Centaur. We took advantage of this incredibly rare planetary alignment of Jupiter, Saturn, Uranus, and Neptune, where one spacecraft, there we're putting out the booms. On the left is the nuclear battery, RTG. The right is the scan platform with all the cameras and stuff. And the gold disc there is the gold phonograph record, LP, vinyl. So it has the greatest hits of Earth, readings, languages, pictures, music, sounds. This alignment of the four gas giant outer planets, Jupiter, Saturn, Uranus, and Neptune. We're coming up on a Jupiter-Saturn alignment here. Going to be incredibly close, closest for centuries. And be sure to check that out. But we had all four gas giants lining up on the same side of the sun. That only happens every 176 years. So this happened in 1977. And someone went to President Nixon in the early 70s and said, now look, All the gas giant planets are aligning. In 77, we can get one spacecraft out to Neptune. There's Io, the erupting volcanoes of Io. See them in the upper left? Crescent Io. So crazy discovery there. Europa, this ice world of Jupiter with a global subsurface water ocean. So he told Nixon the last time, and here we got on to Saturn, 1980, 1981 with Voyager. So they told Nixon, now look, if these planets are aligning, you could approve this mission. The last time the planets aligned was 176 years ago, 1801, and Thomas Jefferson blew it. Don't make the same mistake. And Nixon said, let's do two. And then we were just flown by Uranus there, January 1986, the only spacecraft to fly by Uranus, Voyager 2, and went on to Neptune, August of 1989. Ordinarily, it takes 30 years to get to Neptune on a home and transfer orbit. There we're diving over Neptune, North Pole, and there's Neptune's moon, Triton, barely above absolute zero, active nitrogen geysers, a crazy place in the outer solar system, geologic activity. So thankfully Nixon said yes. We did the Voyager 1 and 2 spacecraft in 1977. They did their planetary flybys in the 70s and 80s. They're still going. They're 43 years old. We still talk to both spacecraft every day. You have a unique capability. Voyager 2, I'll show let's go ahead, Michael. I think we're good on the video here. So there's the tour. See, the sun now is a white ball, and we launched out Voyager 1's in blue, Voyager 2's in red. Voyager 2 launched first. That drove the press crazy, but it was slower, so Voyager 1 overtook it, got to Jupiter first. So that's the only reason we did that. Now look at Voyager 1. When it flew by Jupiter and then out to Saturn, see how it takes a turn very north? It's going up above the ecliptic plane. That's so it could hit the moon Titan. And that precluded it from going on to Uranus and Neptune, which are in the ecliptic plane. But Voyager 1's really far north. Voyager 2 then could go on from Saturn to Uranus to Neptune, which it did. But it's actually heading very far south now. And that's bad news for us in the Northern Hemisphere, but it's great news for Australia. It means you have the only antennas that can talk to Voyager 2. And in fact, there's only one antenna, Deep Space Station 43 in Canberra, that can send commands to Voyager 2, and it was down from March, and it's still down. So Voyager 2, we still get tracking downlink, but if Voyager 2 had a problem, since March, we can't do anything. We'd have to sit and watch the spacecraft die. And I'm thrilled to report about a month ago, we did a test. They've refurbished the antenna, did a test to see if it could now, that it's fixed up on Voyager 2, and it worked. So we're able to, thank you, Australia. Thank you, Canberra. So we are back in business. Now we can control Voyager 1 and 2. Next slide, please. And I believe that's out at Canberra. So on a beautiful foggy morning, the dish at lower left is DSS 43. And by the way, the dish is one of my favorite movies. I absolutely love it. And I watched it on the 50th anniversary of Apollo moon landing when I was down in Australia in July of 2019, last year. Beautiful shot there. Next slide, please. Okay, why are we still going? The planets are long behind us. Look at this, Voyager 1 and Voyager 2, they're in interstellar space. The sun blows a little bubble around itself called the heliosphere, and we've crossed the termination shock in the heliosheath, or the heliopause, and we're the only two objects in interstellar space. We didn't know what's there, so now it's not the sun's solar wind that dominates, it's the interstellar wind. And we're still talking to both spacecraft. Next slide, please. That's a couple weeks old, but look how far away they are, 43 years since launch. They are, good, we've got it in, I should have put it in God's units, which are metric units. It's in miles, apologize for that. So it's about 21 billion kilometers away for Voyager 1, 22 billion kilometers away, and then about 19 billion kilometers away for Voyager 2. We have it in AU there, 152 astronomical units from the Earth, and 1 AU is the distance between the Earth and the Sun. Look at the one-way light time. The signal coming from Voyager 1 takes 21 hours to get here. So if Voyager 1 has a problem, it's 21 hours till we know about it, 21 hours to send a fix back. It's amazing. The speed is, let's see here, kilometers per hour would be like 60,000 kilometers per hour. That's amazing. And we're measuring. Next slide, please. I got to keep moving. I'll run out of time here. I want to have some time. So we'd like to think we're very far from Earth, but we're not. And the only way to feel better about how far away from the Earth we are is to use a log scale. So there's the Sun, Earth at 1 AU, Saturn's at 10 AU. The termination shock, heliopause are about at 100 AU. Voyager 1 and 2 are barely beyond 100 AU. At 1,000 AU, the Oort cloud starts, and that goes to 100,000 AU. That's where these comets fall in from Earth, but we're nowhere near there, right? We've been going 43 years, and we're only 150 AU away. So we're doing 3 or 4 AU a year. The nearest star is a few 100,000 AU. So Voyagers will pass by within a light year of a nearby star in about 40, 60,000 years, somewhere in that range. So we've got a ways to go to even get to the nearest star. And of course, the Milky Way is 100,000 light years across. And the nearest star is only about 4 light years away. So we're a growth industry. You know, if you work hard in math and science, I think we'll have enough of a universe for you left to explore as you get out and head to your careers. Next slide, please. Okay, on Cassini, we took this picture. Twice in the entire mission, the sun was behind Saturn as seen from Cassini spacecraft. Because of that, we could take a 12-hour exposure, 200 images, stitch together a mosaic. That's a real color photo of Saturn. The sun is peeking out at the bottom of the image. It's lighting up all the beautiful rings, but it's not even the best part of the shot. The best part of the shot, 1.5 billion kilometers away, is our tiny blue fragile planet Earth. 1.5 billion kilometers away, 1 pixel across. Everybody you've ever known, everybody that's ever lived, everybody you've ever loved or hated or fought with, all the kings, dominions, glories, powers, fighting for that piece of 1 tiny pixel. Everybody that has ever existed lived out their life on that 1 tiny blue marble. It would behoove us to take good care of that planet. And when I saw that image, I had to think. I did a high school report on an English poet named T.S. Eliot, who wrote Cats, the stuff for Cats, the Broadway musical, as an example. And his quote is, "We shall not cease from exploration, and at the end of all of our exploring, will be to arrive where we started and know the place for the first time." So that's how I felt when I looked at that image. I felt like I knew Earth just a little more intimately and kindly. So if these kind of questions interest you, think about careers in the space field, your burgeoning and wonderful Australian Space Agency, or potentially careers in U.S. aerospace or NASA. And the questions are, how old is the universe? How did life start on Earth? Are there other intelligent civilizations in the cosmos? Did intelligent life start? What's the fate of the universe? Why in 2020 don't we know what 95% of the universe is made of, between dark energy and dark matter? Pretty embarrassing. We've been looking at this stuff a long time. Are we messing up the planet so our kids and grandkids can't live here anymore? If there is intelligent life, will we make contact? Have they learned how to get along with each other? Have they solved the big diseases? Do they have a COVID vaccine yet? You know, these are the questions I would like to ask in the cosmos. So think about that as you go forward with your careers. People have been trying to answer these ancient questions forever. Religion's a great way to answer these questions. Philosophy. Isn't it cool to live at a time where STEM, science, technology, engineering, and mathematics, can actually start answering these questions? I feel so privileged to get to work on these missions of discovery. Thank you for your attention. I'd love to take your questions, and go STEM.
There you go. Any questions? You stand up over there. They want the easy thing for you is you just stand here so they can hear you, because Mike wants to record. This is recording, so we can give you a copy of it when it's done.
All righty. Can you hear me all right?
So Todd, can you hear us?
Yep. 5 by 5.
Awesome. I'm curious, do you believe that we'll advance our propulsion enough before we'll catch up with any Voyagers?
Yeah, it's a good question. So I'm a propulsion guy, and it's kind of embarrassing because I fly 1960s technology all the time. Like the Voyager thrusters were the same ones used on Cassini. You know, The problem with propulsion is just getting things going fast and at a high mass rate. That's what you need to get anywhere quickly. And there are propulsive things that can do that. Some have been tested, some are on theory and paper. So we're starting to use more ion engines, and those are great because they get great gas mileage and can get to high speeds, but they have low thrust. So we need to get to other kinds of electric propulsion, nuclear thermal propulsion, eventually antimatter propulsion, that kind of stuff. Solar sails. There's many, many ways to skin a cat and to get. So what you need to do is look at your mission, where you're going, how long you have to get there, and that dictates what kind of propulsion you need to use. So we'll get there. It's just going to take some time. But there are certainly things on paper that can improve it. But like to get to the nearest star, you've got to get going a pretty good fraction of the speed of light to get there in any kind of reasonable time. And chemical rockets can't do it, and ion propulsion can't do it. So you need things like solar sails or maybe nuclear thermal or antimatter rockets, things like that. So stay tuned. There's lots of work to be done in those areas as well.
I heard that we could reach Alpha Centauri using a ridiculous arsenal of nuclear power, but besides that, what part of Mars 2020 are you involved in?
Michael, I'm hearing this breaking up.
What part of Mars 2020?
What part of Mars 2020 am I working on? Yeah. Yeah.
Todd? Yes. Yep.
Yeah. What part of Mars 2020 are you working on, Todd?
Yeah, I'm the head propulsion guy for operations, which means Genius has built it, and so guys like me can fly it without too much trouble. So, health and safety of the propulsion system, the cruise stage and the descent stage, the rocket-powered jetpack that lowers it to the surface. So really, I started about 9 months before launch, getting ready with testing and tools and all that, and now I'm basically flying it to Mars, and hopefully we'll stick the landing in mid-February. And as far as you mentioned nuclear propulsion, yeah, that could work. Nuclear thermal or nuclear ion engines, because nuclear power is very dense, so you could get very high power that way. That might be one way to get an Alpha Centauri mission going. There's a huge team, and I have a prop team of propulsion team of 3 or 4 people. But yeah, my job is a plumber. It's like a space plumber, health and safety of the engines, the tanks, the regulators, making sure we stick the landing. Doing those TCMs, trajectory correction maneuvers. That's my main job.
One more question. Through your extensive career with what would be your most adverse moment, the one that made you pull the most hair out?
Yeah, that's a great question. Launches are always very nerve-wracking, or these landings. The thing that personally scared me the most was in 2006, because we did a Cassini pressurization where we fired a pyrotechnic device on board that opened up a valve, to pressurize a tank. So it's not like an external explosion. It's an internal little explosion that just opens a valve. But right when we did that, we lost signal from the spacecraft for 5 minutes. And it turns out it was an unrelated ground problem with the antenna. I hope it wasn't Australia. But it emulated us blowing up the spacecraft. So for 5 minutes, I thought I blew up Cassini. So that was a very long time.
Wouldn't have been too fun. That's all.
Is that all?
Yeah.
Okay, is there anyone else?
I've got one.
Yeah?
Yeah.
Go for it.
Yeah, hi, I'm JD. I'm actually the teacher of this motley mob. One thing that when I've taught about gravity assist in the past, what sort of margin of error do you have? How hard is it to hit your mark when you're maybe doing multiple gravity assists, 2 or 3, 4 gravity assists, and planning 5, 6, maybe 10 years in advance? How difficult is that, and what sort of margin of error do you have?
That's a great question. And the answer is actually not much, because if you blow your flyby of one of the Earth, Venus, Mars, or Jupiter, if you miss that altitude, let's say by, I would say probably 10 kilometers or more, you might have lost the mission. So That's a lot when you're traveling billions of kilometers. Now, the good news is we have those TCMs, trajectory correction maneuvers, and we can do incremental improvements, and we know our location in space very accurately with Doppler signal from the radio signal and then range. We timed how long the radio signal takes to come down. So between that, we can actually get our position in space down to a meter accuracy, and we can figure out the speed down to less than 1/10 of a millimeter per second. So that's excellent. But you still then, knowledge is one thing, control is another. You have to control the trajectory to, a kilometer or so. But we're able to do that with these trajectory correction maneuvers. But let's say if you had a problem where the antennas went down and you missed critical maneuvers, then you could miss a gravity assist, and that would blow the entire tour, because you can't really get back on it if you've blown those vector triangles, the trigonometry of the gravity assist. So that's one of the reasons.
Should that happen? Have you still to lose a craft out in space?
We've not lost one due to a missed gravity assist. That is correct. And to my knowledge, neither has any other nation.
I have a question for you, Todd.
I'm just going to, it's less important, but it's still, I'm more curious about it. What's the general consensus among your team at JPL? Imperial or metric?
Great question. So the answer is absolutely metric, because that's what I've been working on metric for 30 years at work. Now, in my whole life, I'll admit, I grew up with imperial, so I still think in degrees Fahrenheit and inches, feet, yard. I still think that way, but not at work. Other than, for some reason, pressure. Pressure in bar is just not used in the spacecraft world. It's in the U.S., it's always PSI, pounds per square inch. But that being said, the U.S. manufacturers still think in English units. Like the rocket manufacturers, it's all pounds force and inches and feet, and it drives us crazy a little bit. But at JPL, we are big fans of the metric system.
So with that awkward interaction with the manufacturers still using old British units, what are some of the worst instances of conversion that have occurred?
Well, I think the clear winner there is Mars Climate Orbiter in September of 1999. As they approached Mars, it turns out they were lower than they believed they could be, but in fact they were so low they burned up in the Martian atmosphere rather than being high enough to fire the engine to capture into orbit. And that was traced to an error with the small force modeling that only mattered when you were deep in Mars gravity well, and it was the difference from newtons of thrust versus pound force of thrust. So, and it was a $125 million U.S. mission loss. So for your students, if your professor takes off because you didn't write your units down, oh, come on, he knew which units I meant. Oh, really, students? I have 125 million reasons you need to write your units down. So give your professors a break. They know exactly what they're doing.
Can I jump in? Sorry. Yeah, the one more question. I just want to say thank you for reinforcing that about the units. I'm going to come back to it.
Todd.
Is the check in the mail for that, by the way?
Absolutely.
Todd, this is Bob. You just want to tell them about the game that you've got at the back of the area, which shows how to do gravity assist. We were absolutely blown away how simple that looks to show the practical application of all those mathematics. So
yeah, I can describe it. I wonder if it's out there anywhere on the web. There's a guy named Dave Doody, Doody, so that's Delta Oscar Oscar Delta Yankee, and he built a machine that actually simulates gravity assist by using magnets. So it's like a little pinball machine type thing, and I bet you there's a website. I don't know if anybody. I could take the time now, but I probably should focus on Q&A. But maybe we can find a website and post a link or something.
I think I took a picture of it while we were at JPL, Todd.
Okay.
I'll share that later. Okay.
All right, that sounds good. But yeah, it's fascinating, Bob, and it's because now gravity's an inverse square force, magnetism's inverse cube, but it's close enough for government work. and it does work. So you spin this Jupiter turntable around, you fire a marble out, and if you time it right, the marble flies by the rotating Jupiter, and because of the magnetism, it pumps up the little rolling ball, which represents the spacecraft, to get out to Saturn. And you can see if you launch it without that gravity assist, it doesn't have the launch energy to get to Saturn. So it's a perfect analogy, and it's just really cool. It is not a JPL anymore, by the way. So I think it's a planetary science, a planetary society headquarters in Pasadena, is what I've heard.
Oh, did it get moved?
Yep. It was not in a publicly accessible area at JPL anyway. It was only on some of these private tours that one got to see it. But I think it's at the Planetary Society. It's very cool.
Is Earth one of the parts when launching a rocket, like all the variables you have to take into account after getting out of Earth's atmosphere?
Can we get you to repeat that? You broke up in the middle.
Yeah.
Is Earth the part of Earth launching a rocket, like all the variables associated with the planet?
Yeah, it's kind of a pain because you have to. Of course, we pick launch sites. There's clever things you can do. You can launch near the equator, and you can go east because the Earth is going like 1,600 kilometers per hour east at the equator due to Earth's rotation. So that cuts about 6% off the requirements of getting into orbit. It's a very clever trick. So we do it by going Florida, kind of close to the equator, and launching east. You also don't want to launch over people. That's why we launch from our east coast out over the Atlantic Ocean. That's why your new Australian Space Initiative is up in Northern Territories there, launching out over water. So you've got to launch at the right time. Then also, you got to deal with Earth's atmosphere because that could burn up your rocket. So you throttle down the engines and then throttle up when you're higher up. And you got to time it, to meet your planetary requirement or meeting up with the space station's orbit or what have you. And also, among the terrestrial planets, Earth's the heaviest planet, so it's got a pretty big gravity well. So we need these giant rockets and staging and all that to fight Earth's gravity. So we and JPL doesn't do launch vehicles, but we let the rest of the people, and a couple of billionaires like Elon Musk and Jeff Bezos and Richard Branson want to compete to see who can make the cheapest launch vehicle. We're all for that. You go play your little boy games and give us the cheapest launch vehicle you can. Thank you. But seriously, what SpaceX and Blue Origins and Virgin Galactic are doing is absolutely amazing, and we wish them well. And space is huge. There's room for JPL to do what we do and the private biz to do what they do, and it's very exciting.
Just another question. Like, hypothetically, how far away do you think we are from Mars colonization?
Yeah, that's a good question. Now, I mean, NASA officially is planning to Mars missions in the 2030s, and I think it'd be a rotating, continuous kind of thing. So if that counts as colonization, then not that far. About having dozens to hundreds to thousands of people, I think it's going to take decades more. Unless, Elon Musk is a disruptor in this in the best possible way, right? He has very ambitious timelines, and he may drive some of these kind of considerations too. So it's an exciting time, especially thinking to be a student of your age. You will probably see this in your lifetime for sure. Very exciting stuff.
All right, thanks, guys.
You got it.
And so, Todd, that kind of is a good lead into your good friend who was announced yesterday, an anonymous astronaut. So do you want to tell us the story about how you fattened her up?
I will. So Stephanie Wilson is the second African-American woman in space, and she's a good friend of mine. I was going to MIT in 1988 for my senior year, and then she was actually going to Harvard in the same age as me. So Harvard and MIT are only about 3 kilometers apart. So she actually came down the street and took a class with me, and I don't remember meeting her in college, but later we worked together on Galileo mission to Jupiter. She was an attitude control engineer, I was a propulsion engineer. And we became very good friends, and then she applied to the astronaut corps, and I said, that's great, good luck. And I'm thinking, she'll never get it. There's 10,000 applicants for 20 spots. But she made it. And she got selected in 1996 to be an astronaut. And I got very sad. I said, "What?" She said, "Why are you sad?" "Well, you're moving to Texas. I'll never see you." And she says, "You're one of my best friends. I'm not going to forget you." And she said, "I want you there when I launch." And it took her 10 years, but I came not once, not twice, but 3 times to Florida and watched her blast off on the space shuttle, and then emailed her on orbit, and took pictures of her flying over L.A. at 25,000 kilometers an hour, and got a picture of her and a palm tree and Jupiter in the same shot, because we worked on Galileo Jupiter mission together. But she almost didn't make it, because when she got picked to be an astronaut, she had 2 problems. She couldn't swim, and I was like, just float, because I'm a chubby guy, right? So I float real easily, and she's super skinny, so she just sinks to the bottom. And I was like, just find your inner fat girl. Floating's easy. Well, she couldn't do it, but she got swim lessons and finally could float. But her second problem was related. She was too thin. She weighed 105 pounds dripping wet, which is like 60 kilos, something like that. 65, somewhere in there. No, probably less. 50 kilos. That sounds about right. And they said, if you can't gain 2 or 3 kilos and keep it on, you're out, because you're too small for the extra small NASA spacesuit. She said, I don't know what to do. I can't gain weight. And I was like, again, different species. I don't know who you are. I don't relate to you, but I can help you, because I love to bake, and I make killer chocolate chip pecan cookies. So I started making it and giving it to her, and I said, don't gorge yourself, but just eat a bunch of them every day. When you get low, let me know so I can bake more, and I'll ship them to you in Texas. And I kept baking cookies for her, and she put on 3 kilograms like that and never took it off. And so that's my contribution to human spaceflight, is fattening Stephanie Wilson up so she could fit the NASA extra small spacesuit. And every time she flew, reporters found me and asked that story, and I tell that story every time. But now, just yesterday, she was picked to be one of 18 Artemis astronauts. And because of that, she has a very decent shot at becoming the first woman to set foot on the moon. And I'll know my cookies got her there in 2024 or whenever it happens. So that's my Stephanie Wilson story.
So probably 1 or 2 more questions, and we'll wrap it up for you, Todd, because we know you've got to do that other gig. So
I can stay on. I'll go log in, but that's been pretty quiet, and it depends on the students there and their availability. But I'm happy to stay on for questions and answers.
Okay. All right. That's cool.
Michael's availability too.
Yeah.
I will be available. And Jackie, this young lady in the front, just in front of me here, has raised her hand a few times. If we can get her in next. Thanks.
Good morning. So my question is, how far do you think you're away from developing an engine that has the capacity to complete both atmospheric orbits and atmospheric orbits repetitively? So like orbit Jupiter and then take itself elsewhere to orbit somewhere else and even land and then relaunch itself.
Yeah, that's a really great question. So orbiting a couple of asteroids, even the 2 biggest ones, is tricky enough. Trying to orbit Jupiter or Saturn and then spiral out again, it's really tough, because those gravity wells are so deep. So you can't really think about probably doing that with ion engines. You need something with really high, what we call ISP, specific impulse. In other words, like the gas mileage or the exhaust velocity of the rocket. But you got to have really high thrust too. So now we're into things like maybe nuclear thermal propulsion, other kinds of electric propulsion that have high thrust, maybe nuclear ion propulsion, maybe. But again, you'd need a ton of ion engines. So I think it's not so much the technology hurdles. It is, but it's really a funding thing. So if you build the mission, if you show me a mission where you need that propulsion, then the dollars would flow into the development work needed to build that propulsion. And we don't think there's huge showstoppers to get there. It's just a matter of funding priorities, national will to do so, and the mission profile. So, eventually I would see that like if you want a human solar system tour mission. Because if I got that capability, I wouldn't want to stick to one planet. I'd want to go check them all out. That could then drive that propulsion engine development that would be needed. But it's a good question. I fear the answer is decades off, because I've not seen those kind of missions talked about. But maybe within your lifetime. Maybe we see that. That'd be great. That's a good question, too.
Yeah, thank you.
I've got it's not very an important question really, but it's more, what was your favorite mission and why was it your favorite mission? It's not really an important one, but yeah, it is. So Todd, what's your favorite?
Yeah, I actually love that question. I've got that question before, and it's kind of the cop-out answer of like, I love all my children, I can't pick, but I have favorite ones for different reasons. So I'll give those. I love Galileo because it was my first job, and because I love Jupiter and telescope and the Voyagers flying by Jupiter I saw in National Geographic magazine, and just to think I was flown right in on the Galileo flight team. By the way, a mission that had tons of problems. So it was a great education for how to be an engineer and solve problems too. So I love that for that reason. Cassini just for how smooth it went, and that was my first lead role, and for how long it went. And that picture of Earth from Saturn and all that. So that's a favorite. Your first Mars mission you never forget because of the thrill of the landing, the audacity of, hitting the atmosphere and bouncing, and because it's this instant payoff. Jupiter or Cassini, Galileo took 7 years to get out there, and you got to be very patient. A Mars landing is only 6 to 9 months from launch to landing, so it's this instant gratification feel to it. And then Dawn was my first electric propulsion mission, so I love that. For just the kind of the teenage boy in me, Deep Impact, where we crashed into a comet, made a big explosion, that was just cool. So that was back in 2005. I love that one too. But I think the one that drives my passion and SMAP too. I have a very bad carbon footprint, at least when I was flying. It's nice to give something back to the Earth that I take so much from. Actually help with some Earth science, So SMAP is important for that reason. But, I'd have to say probably Voyager, just because it's my childhood dream job. And I feel more like a poet than an engineer on that mission, because that mission inspires me, it fuels me, it drives my passion, and because of Gold Record. And it will, if we screw things up on this planet, such that we can't get along and somehow destroy the planet, those 2 Voyagers may end up being the only proof we ever existed as humans. And that just blows my mind. And that's why it's like a first date with the universe. We showed them only the good stuff, no war, disease, famine. We'll show them the ugly sides of humanity later. You always own your behavior on best behavior on a first date. So the awesome responsibility of keeping Voyager alive and knowing it will outlive the Earth and the Sun. Billions of years from now, Voyagers will be circling the center of the Milky Way galaxy. So for me, I think that's the mission that just speaks most to my heart.
Yeah.
Todd, you mentioned the gold record a couple of times. The kids may not know what the significance is.
The kids might not know what a record is. So, so what happened is someone realized, remember all this gravity assist stuff. So by the time you fly by Jupiter and Saturn, and especially then Neptune and Uranus and Neptune as well, Voyagers have solar system escape velocity, which means they'll never see the sun again. They don't have Milky Way escape velocity. So like the sun and the Earth, they are doomed to forever orbit the center of the Milky Way galaxy every 225 million years. However, because they'll never see the sun again, over billions of years, they will encounter millions of stars. So Carl Sagan and others recognized that the spacecraft, since it was leaving the Earth, we need a calling card. And the pioneers had a plaque on them, but, what's really hip and cool is music. So in the mid-1970s, we took the greatest hits of Earth, music from Aboriginal tribes, every corner of Earth. There are no corners of Earth, not a flat earther. I want to make that abundantly clear. It's a sphere. But anyway, there's greetings, pictures, languages, sounds, music from planet Earth, all 2 hours worth put on a gold phonograph record that's on the side of the Voyager spacecraft. And we sent the needle and the record and a stylus. They have to build their own stereo and speakers. But if they're smart enough to find a cold hunk of dead metal, they're smart enough to build a stereo. And it was the hidden agenda of Carl Sagan was world peace. This brought the Earth together. This wasn't the U.S. sending out a calling card. This was the greatest hits of Earth as of 1977. And the record producer, they had 5 weeks to make it. And he said, I got into the music biz. There were exactly 2 copies of my record made. Both of them were unceremoniously jettisoned from Earth for all eternity, so I got out of the music business. But but you can buy replicas of the record, and it's just gorgeous to hear how we thought and what our hopes and dreams were as of 1977. The record also, the cover of the record, they won't know how to play a record, right? But it shows them how to play it, how to get the pictures off it, but they don't know what an inch or they haven't picked between imperial or metric. They don't know what an inch or a year or a foot or a pound or anything is. So we use the size of the hydrogen atom and the transition time of the hydrogen atom for our length and time scales, because those are constant across billions of years and billions of light years. So it's a real clever way to get a scale they can understand. We also showed them a pulsar map with 14 pulsars that rotated at very fixed frequency with the frequencies in binary in terms of the hydrogen atom frequency. So they should be able to triangulate, figure out where it came from. Some people were mad. Why are you sending them directions to 5 billion tasty edible humans? Well, I guess we're doing that. My comment would be that's an awful long way to go for takeaway. So the aliens would probably be better to eat local. That's like farming local, right? Eat local there. But anyway, it is a beautiful piece of humanity and will long outlive us and even our home planet and our home star.
So for those of you paying attention, I did bring up an image for you of what it looks like.
All right, this is creating more questions.
And please keep going. I'm signing into my other meeting, but again, I'm sure it will be quiet because I've not seen a peep for days. So I'll just say I'm here and I'll watch the chat over there. But it's absolutely no worries here. Let's see here.
Give us just a second, young man. We'll be right with you. We'll let Todd finish dialing in.
So what do you guys think about the technology we're using? These guys, it's dinner time yesterday in Los Angeles. They're sitting in Pasadena, and we're having an absolute closed discussion, Q&A, right across the world.
I love the technology. It's just so great. Okay, I think I'm in my meeting and nothing yet. Somebody did give me a little shout out just to welcome me aboard, but I will watch that chat box. But I'm back to your regularly scheduled programming. This is much more fun for me. I love taking questions from the students, and I think this might sound like a cool job, getting to play with spacecraft and fly them around the solar system.
I think they're thinking it's a pretty cool job. Yep. So when SpaceX landed their rocket, how did you feel about the possible advancements that NASA could make in the near future?
Yeah, that's a good question. So, and of course, yesterday's little snafu notwithstanding, no problem. These things are hard. The press, of course, just shows the explosion because it makes good TV. But all the rest of the Mars rocket tests went perfectly. But for years now, SpaceX has been, you look at the economics of it, and you can convince yourself it makes sense to get a cheap launch vehicle to have reusable parts. And I understand the physics of it, bringing them back and landing softly. It's still cool, though. Even though I understand what they're doing and why they're doing it, it still amazes me that they're able to pull it off. So, we can look at that where it makes sense. I think I don't know too much about SLS, which is NASA's new heavy lift launch vehicle. It's going to replace the shuttle. I don't think it has any of that kind of landing stuff on land. There's probably recoverable booster stuff out in the Atlantic Ocean, just like we had for the shuttle. But yeah, it's cool. And, if you launch enough, it ends up making sense. And if you don't have to refurbish them very often and can truly make them reusable, that's a great way to get costs down. And they're solving the technical problems of sticking the landing with the boosters coming back. But it makes great TV and video, gets people fired up about it too. So I think it's exciting. And with the amount of launches they've had and the success rate they've had, I think it's here to stay, and it seems to make sense for them and fun to watch, and keep it up, SpaceX.
I was shocked at how many launches and landings they've actually succeeded in so far.
Yeah,
I didn't have been so many.
Yeah, early on, like NASA did in the 60s, they had their share of failures, and others will surely still come. That's nature of the business. The famous quote is, you know how you make $1 million in the private rocket business? You start with $1 billion. So,
All right, just on the topic of SpaceX and Lord and such, are there any significant instances where your team at JPL has collaborated with such institutes?
There is, and it's mostly, so it's probably not too well known, but NASA has pumped millions of dollars into SpaceX over the years, tens of millions, I'm sure, to help get them seed funding to get started. And the payoff for us is as I kind of cheekily said earlier, is cheap access to space. Because launch vehicles cost is a big chunk of our costs. Now, there's questions of, what are they doing? Is it duplicating SLS? And, JPL's not so involved in that. That's other parts of NASA it makes sense to me that NASA would want to have their own heavy lift launch vehicle. They'll have different missions. We don't need to turn a profit, right? Elon Musk eventually wants to turn a profit. He's got a company going on. But where we've partnered with SpaceX mostly at JPL is we've used them for launch vehicles. For cheap launch vehicles to get our stuff into orbit, including then payloads that have gone to the space station, because JPL's built some science payloads that are on the station right now. The cold atomic clock or something. I think that's one. It's very exciting stuff that was launched on a SpaceX rocket. So again, we wish them well. We're excited, and we are happy as they demonstrate the reliability as they've been doing. We're happy to use them for launch vehicle contract services. Just so the cheaper our launch vehicles get, the more science we can launch into space on a fixed budget.
Yeah, that's pretty good.
Yeah, Todd, kids often ask me about space junk and how much space junk is in orbit there. How worried are you about becoming redundant from the amount of space junk and therefore things becoming too dangerous?
Yeah, that's a great question. So I never used to worry about this before much when I was on the planetary side of the house, but now that I'm on SMAP, this Earth orbiter, now I know really how messy Earth orbit is. And the problem is it can grow exponentially if you have a few crashes, because it makes so much more debris, which then eventually, can lead to trouble. So I think this is a problem just ripe for fixing with private industry. They may be able to be contracted to figure out how to clean up space junk. That would be, now to me, as a science guy, frankly, I would find that work as boring as being a trash collector on Earth. I'm all about the exploration. So I'm glad there's people that would want to do that work, but I have no interest in it personally, other than just get it out of the way so my Earth orbiters will not be damaged. I'm less worried about it in the planetary side of the house, right? Because there's just nothing out there in the vastest interstellar space. Where we've had to worry about it is things like Saturn's ring debris and getting through the asteroid belt and things like that. But it turns out the asteroid belt's pretty darn empty. The gap between Saturn's rings is pretty empty. There's some dusty rings out at Saturn and the other gas giant planets. But luckily, and this is natural debris, not, human-made space debris like we have in Earth orbit. So a big problem that's going to get worse, and then hopefully private industry would take on some, find a good way to make a profit cleaning that up and making everybody happy.
So Todd, mate, just confirming we've got you booked for March, haven't we?
Yes, I think you had said you'd like to talk to me after the Mars Perseverance landing, and that should be okay. It's been pretty crazy since July juggling these 3 missions, and at the moment I'm not picking up anything immediately right after Perseverance. So I should be back to just Voyager and SMAP after March 1st or so. Hopefully with good
They don't
news.
have you on SWAT, huh?
They don't. Is that going to be flown out of JPL? Do you know, Michael? If so, I suppose I might end up on that as well.
I think it is, but Don't quote me. I might not be wrong on that, but I thought that was coming out of JPL.
I believe, I know it was built there, and I would imagine it probably will be flown here as well. So that'd be interesting. If I could pick up SWAT, then I could probably fly SMAP and SWAT kind of in parallel with each other. And again, it would help ease my guilty Catholic conscience again for having a horrible carbon footprint.
Exactly.
So that would not be bad. But we'll see. But right now I'm kind of, as much as I want to keep SMAP and Voyager flying well and worry about them, I'm kind of laser focused on Perseverance right now because we've got to stick that Mars landing. And stay tuned for that. It'll be, I think, early morning on Friday, the 19th of February, 2021 in Australia time.
Australia time. It's 12:50 p.m. the 18th our time.
Correct. So
all right, well, we're going to wrap this up, and we're going to thank you so much for your time. And Mike Kimes, are you available for March too? Because we keep saying Todd, hopefully you're available.
We'll make sure that we get it all squared away.
Okie dokie. Well, thanks so much, team, our wonderful team in NASA JPL. Thank you so much for your time. And I'm sure there'll be other questions, and I know that you guys will be all right if we just email them. And it's been a lot of fun.
Pleasure's all mine, Jackie, and be delighted to take any further questions.
All right, we're going to email them to you because we have to wrap up. These guys have to go and do some other stuff. All right? So love to you both. Thank you so much, and we'll talk soon.
My absolute pleasure, and if I've kept one kid out of law school, it was worth it.